So as we enter the second half of our calculus course, we're going to look into the area problem as opposed to the slope at a particular point problem. So this area problem is concerning how would we determine the area of a region. In this case, it's bounded by, in the first quadrant, by the curve 1 minus x squared. And what we're trying to do is capture that exact value of that area, which is a very irregular shape. It's nothing like anything we did in geometry where we use squares, rectangles, trapezoids, whatever the case may be, circles, anything like that we know a known formula for the area. So in class we talked about how we could break this interval from 0 to 1, which is where the x-intercept occurs, into, in this case we use 6 equally width segments or widths of what are going to form the basis of rectangles, and we said we could determine the area of each of these 6 rectangles as we move across. It would not be a very accurate approximation for the area because we have all this extra area up here. However, it's very calculatable. We were able to go through pretty quickly, and with the aid of a calculator that can add up the sum of a sequence of numbers, we took the area of each of these differently colored rectangles, we added them together, and we got an approximation of something like about 0.7 or 7/10 of a square unit. And then we said, well, what if we use an underestimate? We kind of used rectangles that had their heights determined at the right side of the rectangle, so we were kind of coming up underneath the curve instead of extending out over it like we did in this first example. And we found an estimate, I think it was somewhere in the neighborhood of about 0.58 tenths or 58/100ths of a square unit. Then we did a midpoint approximation where we checked the height of these rectangles at the middle of their width, and we had the calculator perform that for us. And we got an approximation that was clearly better than the other two, but it's still just at an approximation. So one of the primary questions of integral calculus is how do you determine the area bounded by a curve given by some function and, say, the x-axis. So in order to make a little discovery about how we're going to determine this area, we wanted to take a look at a very regular shape, but yet still a shape that's bounded by a quote-unquote curve. This line, we're using 4x plus 1, y equals 4x plus 1, as what I'm going to refer to as the border curve for this region down here. Now the region is bounded at the x-axis here below, and we're starting at x equals 0, and we're extending out to some random point x. Now, for example, if x was 3, we'd come out from 0 to 3, and we would come up straight there. And we realized that that orange shape that we have there is basically just a trapezoid. So we took it and rotated around and recognized that this is a shape that we do know the area of. We have a formula for the area of a trapezoid that we learned in middle school. It's the average of the bases, b1 and b2. So the sum of b1 and b2 divided by 2, or multiplied by 1/2, and then multiplied by the height. Now, the interesting thing about this is this top base that I've referred to as B2 here is just this little vertical piece, which is just the y-intercept of that line. So that piece is going to be 1 unit long. So that's where this 1 comes from. Now, the bottom base, 4x plus 1, what that's referring to is this piece over here, which if you, say, went over to 3, x equals 3, and you wanted to find out how long this side was, you'd plug 3 into this, 4x plus 1, and you would get 4 times 3 plus 1 would be 13. If you went over to 4, you'd come up here, and you would be at a height of 4 times 4 plus 1, which would be 17. And if you went over to 7, you'd put 7 in for x. If you went over to 10, you'd put 10 in for x. So we're going over to x, so our height is simply, the length of this piece is simply going to be 4x plus 1. So that's itemized down here. And so the sum of b1 and b2 is 4x plus 1 plus the 1. We take the average of that, and then this vertical, what turns out to be this vertical height here is really this horizontal distance here, which is x units. We went over x units. So we could say this height right there is going to be x. So we've got that right there. Now, when we simplify this, we get 1/2. 1 plus 1 is 2, I'm pretty sure. So we get 4x plus 2 times x, and of course 1/2 of 4x plus 2 is 2x plus 1 being multiplied by x, and distribute that x in there, and we get 2x squared plus x. And I want to be clear that this expression right here is a formula for the area of this region at any x value. So in other words, if we went over 5 units and came up and built that trapezoid, the value of that area would be given by 2 times 5 squared plus 5. You just plug 5 into this. So this function will spit out an area for this thing for any value of x. Now, just as a curiosity, why? Well, because I know the answer. What happens when we take the derivative of that area function? We're going to get 4x plus 1. You might say, well, 4x plus 1 sounds familiar, and it sure is because it was the border curve. It was the equation of the border curve. So that may just be a coincidence, but probably not. And as it turns out, that is indeed always going to be the case, that if you happen to know the area function, we'll call this a of x inside there, its derivative will be the border function. But if you remember how this problem started, it was we want to find the area function based on a given border function. So I'm curious if there's a process that if we don't know the area function, if we only know the border function, could we work backwards and say if the derivative of the area function is the border function, then maybe going backwards, the antiderivative of the border function will be the area function. So that's our kind of premises, our premise, our hypothesis, if you will. So we want to try another experiment with this same function, 4x plus 1. But in this case, I'm not going to start over here at the origin. I'm going to start here at x equals 2 and then move out to some random x value. So if you could imagine if x was 5, let's say we went from 2 out to 5, of course that distance would be 3 units, right? 5 minus 2. So if we start at 2 and we go over to x, that distance will be x minus 2. All right, so as we look at that trapezoid turned kind of on its side, like we did in the previous example, really horrible drawing there, but we would see that this vertical piece on this side is still going to be given by 4x plus 1, and the top piece now is going to be this guy, which is the height of that function at x equals 2. 4 times 2 plus 1 is 9. And then this piece down here is going to be our height over here, which is going to be x minus 2. So if we think about the formula for that area, we've got 1/2 the sum of the bases, which is 4x plus 1, the bottom base, plus 9, which is the top base, multiplied by this height, which is x minus 2. And this is going to be 4x plus 10. When we take half of it, it's going to be 2x plus 5. And look at that with x minus 2. Foil those two together, we're going to get 2x squared. We're going to get positive 1x, and we're going to get minus 10. Now, it's interesting to note, 2x squared plus x minus 10 is a lot like the 2x squared plus x we got up here. And if you think about where this minus 10 come, in other words, this area appears smaller than that area, well, the reason it does is because we've cut off this back little trapezoid there, and guess what? The area of that piece that we've left behind that we've cut off is going to be 10 units. So 2x squared plus x minus 10 just reflects that we've subtracted 10 square units of area from that piece right there. However, does our supposition hold true that when we look at this area function, if we were to take its derivative, sure enough, we still get 4x plus 1. So despite the kind of like the movement of our area, it's not exactly the same region as it was up here, its derivative is still the border function. So the moral of the story here is that if you have an area function that's predicting the area of this thing, you could take its derivative rather, and it would be the border function, which I'm going to call f of x, just some generic function that's bordering our curve. However, that's kind of if that was the problem, it wouldn't be a problem because we already know how to take derivatives. But here's the thing, we're only going to have the border function, and so what we're going to work to do is go backwards and figure out what this area function is that has this function as its derivative. So we have one more example here where we have a linear function which is given by y equals 2x minus 3. And again, we're going to try to obtain a region, or a formula for the area for that region. And it looks like we're starting at, well, let's see, x equals 3 here, and we're moving out to some random x value. So I'm going to leave that exercise up to you to use the same technique we just did to get the area of this thing in terms of x, using the formula for the area of a trapezoid, and then do a little experiment and see if the derivative of that area function gives you 2x minus 3. And if you do everything correctly, it certainly should. So we look at our conversation, our vocab here, and we've realized that because we're not going to have the area function when this border curve becomes something like really a curve. Imagine we had something like this where the curve is really, undulating, and we're trying to capture area bounded by that curve down in here. Well, we can't use, a simple trapezoid formula. What we need is some calculus, and that process is going to be using the antiderivative. And this process of finding that antiderivative, going backwards, the reverse of differentiation, is called antidifferentiation, but more commonly just referred to as integration. So you can kind of use the antiderivative and an integral kind of interchangeably, and antidifferentiation and integration kind of interchangeably. And generally, we're gonna use integral and integration more often than antiderivative and antidifferentiation, just because, hey, it's fewer syllables. So as we move into section 5.2, we start our kind of formal study of integration. And we want to first recognize one little challenge that this will present. For example, an antiderivative is kind of finding a function whose derivative is a known function. So for example, if we had the function x to the fourth, and we were trying to find a function that has x to the fourth as its derivative, I think you'd agree that all these functions, these four functions listed here, you know how to use the power rule well enough to know that the derivative of 1/5 x to the fifth is going to be x to the fourth. And the derivative of 3 is just going to be 0. So you wind up getting the derivative of x to the fourth. However, the second example also has a derivative of x to the fourth, because you're realizing that anytime you take the derivative constant, it just goes to 0, so it doesn't show up in the derivative. So what we have is are virtually infinitely many possible antiderivatives for x to the fourth. However, the thing that's going to be common about them is they're all going to differ by just a constant. Whether the constant is +3 or +300 or -2 or 1 or 0, they all have this common element of the 1/5 x to the fifth. Similarly with cosine, we all know that the derivative of sine is cosine, but the derivative of sine of x plus 4 is also cosine. So again, as long as our function here only differs by a constant, we can rely on the fact that it's going to have a common derivative. So the notation we're often going to use is kind of like the big function, the mother function, if you will, being this capital F is often used to denote that its derivative will be this lowercase f. So just kind of get used to that notation, and they'll often describe it in problems on the AP exam. They'll describe a function where capital F prime is lowercase f. So looking at the graphs, this should sort of make sense that all these graphs, which just differ by a constant, are just vertical shifts of each other. But if you take an example of look and see what's happening at, say, -1, you should be able to realize that at -1, all the curves kind of have the same tangent line, which again is what the derivative is predicting, the slope of that tangent line. So the slopes are consistent throughout those four curves. They're just vertical shifts of one another. So the way we deal with this ambiguity of like not knowing what this constant might have been after taking its derivative is when we find an antiderivative, we kind of need this formula, this specific function that has this as its derivative, but we demonstrate that we don't know what the constant could have been by adding a plus c at the end of it, just to indicate there could be some constant there that's unknown to us. So it's kind of important that we do that to indicate the lack of specificity, that we really don't know exactly what that function might be unless we have some clues about that function, which we're going to see shortly. As far as the notation goes, we're going to use this symbol here. Kind of looks like a big skinny S to indicate the antiderivative of some function, for example, 3x squared dx. And we talked briefly on our first day about how when we were coming up with the formula, or not the formula, the numeric value for the area bounded by that curve, 1 minus x squared, and we built all those rectangles, we were doing the sum of a height and a width. So we were building areas of rectangles that kind of had different heights and common widths. And we said the problem with the lack of our accuracy in our area approximation wasn't the fact that we were using the left side of the rectangle or the right side of the rectangle, is that we only used 6 rectangles. And we looked at an example where we had the calculator perform the computations with 500 rectangles, and we got a really, really accurate answer. So what's happening here in this expression is saying, hey, what happens when we take this height and multiply it by this width, when the width is not 1/6 of a unit or 1/500th of a unit, but maybe infinitesimally small. And when we talk about infinitesimally small changes in x, we call that dx. So if you want to think of this as a height times a width, and then doing that infinitely many times for infinitely skinny rectangles and getting this expression, that's one way to do it. Or you can just think of it as, hey, this means I'm looking for a function that has 3x squared as its derivative. And the way we describe that most general antiderivative, in other words, the most general function that has 3x squared as its derivative, just kind of an intuitive approach, is that it's going to be x cubed. Now, to indicate that I don't know if there was a constant on this thing, we're going to put a big plus c. So if you're asked to evaluate, evaluate an integral expression to come up with its equivalent, it's going to be some function with a plus c on it. So as you see here in this major concept, the main thing you need to understand walking away from this page is when you see the integral symbol and a function followed by a dx, basically what this is asking you is saying, what function has x squared as its derivative? Or what function has a derivative equivalent to x squared? And of course, it's important to know that that answer is not going to be unique. We're going to have this plus c to indicate the fact that there could be any number of infinitely many different constants that could have that same derivative. But they're all considered to be a family of functions that are going to have a common slope formula. So here we go with the kind of the formal mathematical process that we're talking about of integration. So if we have a function whose derivative, this function big F has its derivative as little f, then you can write the antiderivative, or the integral of little f, is going to be big F plus c to demonstrate that unknown or ambiguous constant that might exist there. It's important to note that the variable that we're integrating across x in this case shows up as the variable next to the d here, the differential of x, which is essentially that really, really small infinitesimal width of our rectangles that we talked about earlier. A few rules of derivatives and antiderivatives. Of course, when you're taking the derivative of a sum or a difference, you just take the derivative of each one individually. So when you're integrating, a function that is comprised of a sum or difference of functions, you just integrate each of them individually. Negative signs are like constants. You can just sort of ignore them during the integration or differentiation process. I always say in class, they kind of just go along for the ride. And now we have a great summary, and I've been talking about this all year when we've been talking about derivatives, is that if you know your derivatives well, you're going to know integration well. For example, the derivative of sine is cosine. So the antiderivative, the integral of cosine, is going to be sine. Of course, you got to put the plus c. And similarly, for all these trig derivatives, of course, the derivative of x with respect to x is 1. So the integral of dx, which is like 1 dx, integrates up to x. You can imagine a little kind of silent 1 there, if you will. This is the one that you're probably most familiar with, but you probably don't recognize. And it's referring to the power rule, which says that, if we have a function where, let's actually call it capital F of x, which is x cubed, f prime, of course, is 3x squared. We can do that on our sleep. And what we've done is multiplied by the exponent and reduced the power by 1. So if we started with a function like 3x squared and we wanted to integrate it or find its antiderivative, the process is the inverse process. So we're going to kind of undo each operation in reverse order. So we're going to take 3x squared and we're going to increase that power by 1 to make it 3x cubed, but then we divide by that new higher power and then simplify if possible. We can cancel out those 3's and have x cubed plus c. So we increase the power by 1 and divide by the new power. So in something like example 1 over here, where we have a difference of two functions, we're just going to integrate each one separately. And so we could write this antiderivative as 3x. We're going to increase the power by 1 and divide by the new power. And then with the negative 2, you could think of that as being negative 2x to the 0. So we could increase that power to 1 and divide by the new power. and add a plus c at the end. And of course, no self-respecting mathematician would leave a 1 up here and a 1 down there. So you would just simplify this and write it as 3x squared over 2 minus 2x plus c. And that's your answer. So as long as we can write a function as a power function, we're just going to increase the power by 1 and divide by the new power. So for something like 3 over root of x, it would be most convenient for us to write this as the integral of 3 times x to the negative 1/2 plus the cosine of x dx. Now, again, you must put that dx there. It really does, an integral expression is meaningless without it. But for this one, we're going to take our 3 and have it go along for the ride. We're going to take our x to the negative 1/2, increase the power by 1, so negative 1/2 plus 1 is positive 1/2, and we're going to divide by that new power of 1/2. We're going to move across here to cosine and recognize that we know that cosine is the derivative of sine, so the integral of cosine is going to be sine. And then put a plus c. The only thing that's kind of awkward here, of course, is this complex fraction that we have. So we'll think about 3x to the 1/2 being divided by 1/2 as being multiplied by the reciprocal of 1/2, which is essentially just 2. So we're going to write that as 2 times 3, which is 6x to the 1/2 plus sine of x plus c. And the good news about integration is once you get your answer, you're like, geez, I don't know if that's right or wrong. I'm new to this. What you could do to check your work is quickly run a derivative. Take the derivative of this and see if you get back to your original expression. I'll let you work on that on your own if you want. Now, these next two cases here both present some interesting situations that are just slightly ramped up versions of these. And there's some challenges presented with these, which I think I'll talk about in class. But essentially, you're going to get the idea, I think, pretty quickly that if you were good at derivatives, for example, the derivative of inverse tangent is 1 over the quantity 1 plus x squared. If you were to see the integral of 1 over 1 plus x squared, if you remember that as the derivative of inverse tangent, you've got your answer. It's the inverse tangent, again, plus c. These problems down here, like I said, have some challenges to them. We can talk about them in class. I would like you to kind of take a crack at those on your own and see what you can do with them, and then we'll move on from there. So now we get to really one of the last types of questions we're going to cover in this section, and I'll finish up this video with this one. It's when we're given what's called a differential equation, which is when we have the information about the derivative of a function rather than the actual function. So in example 5, they're asking us to find the function whose derivative is given by 12x squared plus 6x minus 4, and then we're given this additional clue that the y value of the function when x is 1 is 1. So what we need to do is find the antiderivative. So we're going to set up our integral here, and we'll say that the integral of 12x squared plus 6x minus 4, parentheses around it, dx. So we're going to perform that integration to get the general antiderivative. So with the 12x squared, we're going to increase the power by 1 and divide by that new power. Same with 6x. We will increase the power by 1 and divide by that new power. And then minus 4 will become minus 4x. We increase the power of x from 0 to 1. We add the plus c to remember that we have this unknown constant. And then we're going to simplify this. And as you do more and more of these, you'll kind of do the simplification as you move through it. So this is clearly just 4x cubed plus 3x squared minus 4x plus c. And so our function that we're talking about is given by 4x cubed plus 3x squared minus 4x plus c. However, with this added information that we have that the value of the function at 1 is equal to 1, we can now kind of use that as a clue to figure out what c is. So I'm going to go over here and say that 4 times 1 cubed plus 3 times 1 squared minus 4 times 1 plus c has to be equal to the y value when x is 1, which is given to be 1. So some basic algebra, and we get that 4 plus 3 minus 4 plus c is equal to 1, and so we're going to get that c is equal to negative 2. So the way you express the answer is that f of x must be this function with a c value of negative 2. So 4x cubed
plus 3x squared minus 4x minus 2 is the unique function that has the derivative 12x squared plus 6x minus 4, and also would yield a y value of 1 when x is 1. So there you go, your first differential equation problem.